In this video, we calculate the luminosity of colliding bunches and beams in a particle collider. First, we look at the units. Number of events is given by luminosity times cross-section sigma. The unit of the number of events is just 1. And it equates the product of the unit of the cross-section, which is square meter, so times luminosity, which therefore must be inverse area. Next we write the bunch luminosity of a four-dimensional integral over time and space, which describes how the bunches that are depicted in the figure cross, times the bunch densities, which are normalized to the number of the particles in the bunch, and the luminosity is given by the product of the two densities times the relative velocity. We check the units. There is the integrand, dt is seconds, d3x is meter cubed. The densities have meter to the power of -6, and the velocity is meter per second. If we multiply all this, we find that indeed we get meter to the power of -2 inverse area, which is correct. The relative velocity in a particle physics collider is 2 times the speed of light in the lab frame. Good. We proceed to change the variables. In particular, we change the time integrand to the time integral from t to s0, where s equals c times t. This changes nothing except that we don't need to carry around factors of c. So these are the formulae. Only the product of the densities have to be integrated. We also relabel the c coordinate by s. And now we make assumptions about the density. As we said, they are normalized to the particle number in the bunch, and we assume that the density is a product of 3 densities that only depend on x, y, and s plus minus s0, depending on whether we consider the left or the right moving bunch. We next assume Gaussian distributions. So the x, the y, and the z distribution are given by Gaussian normal distribution with a Gaussian width of sigma x in the x direction, and the normalized density is 1 over square root of 2 pi times sigma x times e to the minus x squared divided by 2 sigma x squared. And the prefactor makes this integral integrate this density integrate to 1 over its support, which is the whole x range. And similarly for the other dimensions in y and in z, which we call s here. So all we need to do is take the 4 integrals and insert. We get the factor of 2 from the relative velocity, the product of the 2 particle numbers per bunch, n1 and n2, and 6 powers of square root of 2 pi in the denominator, and the squared, sigma x squared, sigma y squared, sigma c squared in the denominator from the normalization of the integral. And the exponent, in the exponent we get 2 factors of minus x squared over 2 sigma x squared. So the 2 in the denominator in the exponent goes away. And from the 2 from the distributions in the z direction, we get s minus s0 squared plus s0 squared. Remember, there's a factor of 2 here, so that cancels the 1/2 that's in the definition of the Gaussian. All we have to do now is expand the exponent and carry out the integral. We pull out the constant factors. And we carry over the rest. And we can simplify the dependence on the S coordinate. And now we are ready to perform the integrations. We do this using the normalization integral of the Gaussian width. From this normalization integral, it follows, because there's a factor of 2 not appearing in the denominator in the exponent, so we just put this to the sigma x, and we find that it gets a 1 over square root of, it becomes a 1 over square root of 2. So this integral that we need is just square root of pi without the square root of 2 times sigma x. And now we are ready to carry out 4 integrations all in one go. Prefactors first. We get from the x integral square root pi sigma x, same for sigma y. And then we have an s and an s0 integration with the same sigma z, so that's a squared here. And now all we have to do is cancel these factors. The sigma c's cancels, the sigma c, all the sigma c's cancel, sigma x, sigma y cancel once, so we arrive at an expression of n1 times n2 over 4 pi times sigma x, sigma y. And that's the end result of the luminosity that's coming from one bunch crossing. The beam luminosity is the bunch number times the frequency of the bunch collisions times the bunch luminosity. Briefly say a few words on these numbers. All we have to do is multiply, and we get the beam luminosity. Let's look at the numbers for the LHC as they were designed. These parameters have already been achieved in reality. Typical bunch width in the x and y direction are tens of microns. So here we use 16.7 micrometer, which we write that in terms of a centimeter, because conventionally centimeter is used when quoting luminosities. That's pure convention. So it's 1.67 times 10 to the minus 3 centimeters. Bunch numbers are typically in the range of hundreds of billions. So in this case, per design, it's 1.15 times 10 to the 11 particles in a bunch. And there are 2,808 bunches in the LHC at design, and the revolution frequency of the bunch in the LHC tunnel is 11 kilohertz, which is very, very roughly speed of light divided by the circumference of 27 kilometers. That means we can use these numbers to calculate the beam luminosity, and the result is 1.16 times 10 to the 34 inverse centimeter squared per unit time. This is the LHC design beam luminosity, which has been slightly surpassed recently. Let's change the numbers, let's change the units to reflect the numbers that are conventionally used in high energy physics. One nanobarn is 10 to the minus 9 barn. One barn is 100 square Fermi. If we pull together the powers of 10, we find that 1 nanobarn is a cross-section of 10 to the minus 33 centimeters squared, and hence the beam luminosity is very roughly 1.16 times 10 to the 34 inverse centimeter squared per second, which is 11.6 inverse nanobarn per second. That's the amount, that's the rate that we accumulate data at the LHC. Inclusively, that means integrated over time. During the 3 years of operation of run 2, the LHC has recorded 150 inverse femtobarn, which we can very colloquially write as the time integral of the instantaneous luminosity at the LHC at run 2. So the total amount of data we recorded is 150 inverse femtobarn, very roughly.